Greetings. The problem I want to solve for you today is on the combustion of n-Decane. It is n-Decane, and its composition is C10H22. Now, n-Decane enters our combustion chamber at T equals 298K, which is the ambient temperature. So, on the other hand, we have air. The air that enters our combustion chamber is at 400 K. So air is O2 plus 3.76 N2, and this enters our combustion chamber at T equals 400 Kelvin. Now, we don't know how much air enters, but at the same time, what we want are products which are at T equals 1240 K. So this is a good place to introduce how people control the exit temperature of the combustion chamber. You see, there are two extremes. Two extremes. There are two extremes. First is adiabatic combustion. And that is when combustion is adiabatic and is stoichiometric. All heat produced by the combustion is absorbed by the combustion products, and therefore what we get is the adiabatic flame temperature, which is the maximum temperature that combustion can produce. This is case one. The second case is isothermal combustion. Isothermal combustion. What happens? It's not adiabatic. In fact, we extract so much heat from the combustion products that the combustion products return to the temperature of the reactants. And that is isothermal combustion. And what we conclude from that is the amount of heat that we have extracted is called heating value. Heating value of the fuel. And that's the maximum possible heat one could extract from the combustion of this fuel. Now, there's a third alternative which is more practical, and that is excess air. Introduce excess air. Introduce excess air. What does excess air do? It basically controls exit temperature, exit product temperature. What good does it have? The good it has is that you could control this temperature. Therefore, whatever instrument that comes after this combustion chamber can endure the combustion temperature that is produced. And this problem exactly comes into the category of this third group. Now, we introduce excess air. We don't know how much air is here added, but at the same time, we know the temperature of the products, and therefore, what we want to conclude is that how much excess air should we add so that our combustion products would have the required temperature. Now let's balance the combustion equation. And for C10H22, what we have would be C10H22 plus, we don't know how much air do we need, so X times O2 plus 3.76 N2, and that produces CO2 plus H2O plus, we don't know how much, O2. There would certainly be some O2 since there is excess air, so there would be some excess O2, and plus whatever nitrogen enters from one side, it also goes unattended to the other side. It means that it doesn't enter our combustion process. So O2 plus N2. And now, how do we balance this equation? Is that there is 10 carbon, 10 atoms of carbon, and therefore it would be 10 CO2. And then there are 22 atoms of hydrogen, then there would be 11 H2. Okay, now how many oxygens would remain? There are XO2 added here, and some of it is absorbed by carbon and hydrogen, so there would be 10 O2, 20 here, 11 here, that would be 31, and 31 oxygens. O2, it is 15.5 O2s. There was XO2s to begin with, and minus 15.5. That would be the number of oxygens on the right-hand side. And now for nitrogen, it would be just X times 3.X times 3.76 nitrogen, and that balances our combustion equation. Well, fair enough, we have done our equation. What we need to do is now see how much energy is produced in this combustion. It's adiabatic combustion, and only excess air is controlling our product temperature. Now I have collected all I need for an energy equation in this table. As we see here, C10H22, I have its enthalpy of formation. I don't need anything for its temperature because it enters at 298 and our base temperature is 298. So it would be zero, its sensible temperature would be zero in fact. Now, there are, on the left-hand side, there are oxygen and nitrogen. I have oxygen and nitrogen. Their enthalpy of formation is zero, and their energies at 298 are these two values at 400K they enter. So this is their energies at where they enter. And these are their energies at 1240, where they appear on the right-hand side. Now, the other two elements we have to consider are CO2 and H2O. Enthalpy of formation for them are these two values. Their enthalpies at 298 are here, at 400K they are here, although these two values don't enter our question because all we have is CO2 and H2O at 1240 and not at 400K. Nevertheless, no problem. And here we have at 1240, we have their enthalpies here. So we have all we need for calculating the first law equation and enthalpies of the reactants and also the products. Now let's talk about the enthalpy of reactants. As for the reactants, which is here sigma H reactants equals, there is only one mole of C10H22 and its enthalpy of is only the enthalpy of formation, so it would be 1 times minus 249,659 per every mole of the C10H22 plus, as for the oxygen, its enthalpy is X moles of it, enthalpy of formation is 0, but its enthalpy of uh, its sensible enthalpy would be X times, but that is its enthalpy at 400 minus its enthalpy at 298. At 400, the enthalpy of O2 is 11, and minus its enthalpy at 298, which is 8682, and plus we come to N2, and the number of moles for N2 is X times 3.76 times the enthalpy of formation is, of course, 0, and as for the enthalpy for its temperature, it is 11,640 and minus 8669. 11,640 is the enthalpy of N2 at 400 K, and 8669 is its enthalpy at 298, which is the base set for all enthalpies. Okay, this is our enthalpies for the reactants, and if we calculate them, this would be minus 249,659 plus 144,199.96 and whatever x is, that would be our enthalpy of reactants. Now, let's come to enthalpy of products. As for the enthalpy of products, sigma HP equals, there are 10 moles of CO2 here, and therefore it is 10 times. Now, for CO2, there's an enthalpy of formation, which we have it in the table, and it is minus 393,520. That is the enthalpy of formation, plus whatever it has for its temperature. And now, if the products are going to be at 1240 kelvins, then their enthalpy should be calculated at 1240, and that is 56,108 minus the base enthalpy at the base temperature, which is 9364, and that is the enthalpy for our CO2. That consists of two elements. One is the enthalpy of formation, and then is the enthalpy due to its temperature. Now, next is H2O, therefore it is plus. There are 11 moles of H2O, 11 times enthalpy of formation for H2O, which is minus 241 820, 820 plus, now, enthalpy due to its temperature, its sensible enthalpy is for H2O is 46137, 46137, and minus 9904. That is the enthalpy due to its temperature difference with 298. And now there are two further terms. One is oxygen, which is plus x minus 15.5 times. Now, as for O2 enthalpy formation, zero is only the difference between its enthalpy at 1240 and its enthalpy at 298, and that would be 398.77 minus 86.82. That is our enthalpy for oxygen, and plus for nitrogen, which is 3.76 times X, that's the number of moles, and enthalpy of formation is once again 0. All that is left is 38129 minus 8669. Now, that's all our enthalpy of products. And if we multiply them all together and add them together, this would equal minus 6,185,847 plus 140,229.6 times X. These are the enthalpies of the products. Now, if it is to be adiabatic, the first law of thermodynamics tells us that zero, first law, tells us the problem is steady, so the left-hand side is 0, 0 equals sigma H entering, which is reactants, minus sigma H product. Now we assume this combustion to be, adiabatic, that is Q equals 0, and there is no work involved, and therefore altogether what we have is that there is no heat, there is no work, so sigma HR equals sigma HP. We have calculated sigma HR here. We have calculated sigma HP here, and all we need to do is to put them equal together. Well, now that we know that the enthalpy of reactants equals the enthalpy of products, we may put numbers into this equation, and therefore reactants are minus 249,659, 249,659 plus 141,99.96x, and that equals that of the products, which we calculated it to be minus 6,185,847 plus 140,229.6x. That's an easy calculation, and that gives us x equals 47.1. That means x equals 47.1. Now, from our combustion equation, we knew that if the combustion had 15.5 O2, then it was a stoichiometric combustion. Now that it is 47.1, now if we divide the two, 47.1 divided by 15.5, that equals 3.039. That is, we if we burn our C10H22 with almost 3 times, with slightly more than 3 times uh, theoretic air, then the exit temperature would be 1240. And if we burn it with 2.039 excess air, then our exit temperature would be 1240. Well, thank you very much for watching. Bye.